And greetings. Welcome to the Evidence and Reasons for the Christian Faith video channel, where we explore evidence that supports belief in the Christian faith. This is going to be a nerd torture session, and as the title implies, we're going to cover some really technical things. But it's been my experience for me as a student of science, and this channel does definitely cater to students of science, Christians and professional researchers. Some people have written me privately, and I am just I'm just overwhelmed to find out just the level of education and intellect that is represented in the audience for this particular channel. And that's something I'm very humbled and honored to be a part of, because there's some really very intelligent people, very accomplished and educated people that watch this channel. And I'm indebted to many of them for giving me constructive feedbacks, corrections of my misunderstanding, and teaching me. And it says, I believe it's in the book of Romans, one of the later chapters, that we're able to teach one another. We're able to teach one another. And so greetings to my friends in the side chat. I sent you a Paleologos greetings. I sent you an email to let you know I'd be delighted to see you join. And there's Jordan K. And hope all is well with you. I look forward to collaborating with you. And I was just acknowledging, while you're here, Jordan, I just wanted to acknowledge all the people that have helped me. Like Mr. Jetty 89, I found out he actually works on an accelerator, particle accelerator called a microtron. He said so in one of the comments. And then John B., who's a paleogeochemist, and Jordan K., who's a nuclear engineer. So these are people that have much more knowledge than I do in the topic that I'm exploring. They've been very helpful in giving constructive criticisms and corrections of my misunderstandings. And so I just wanted to acknowledge them. I did want to say that unlike other channels, that YouTube channels that are maybe sometimes organized to try to get as many subscribers as possible or whatever, I'm into quality, not quantity. This channel is actually an opportunity for me to just fellowship and hang out with people I love, and people I feel that I can support, and people that will support me. The success of this channel is not defined by the number of subscribers. But that being said, the number of subscribers continues to grow, and the number of views on my videos continues to grow and to be steady, and I'm very, very grateful for that. I think the way the channel will grow out is as I build a website and I do more apologetics work and start traveling in the country. I'm meeting a lot of colleagues now that Mom's gone home to be with the Lord. I'm able to actually drive around and meet people in person. I've been getting invited to a lot of churches and to do a lot of talks. So for those, most of you know what this channel is about, that it's very critical of evolutionary theory, and it advocates the Young Earth, Young Cosmos viewpoint. With that being said, I am on extremely friendly terms with old Earth creationists. I sometimes see the president of the Institute of Creation Research hang out at the Discovery Institute, which is an old Earth organization. I think it's great we're being on increasingly friendly terms with the old Earth community, the old Earth intelligent design, old Earth creationist community. You know, I basically feel that the old Earth creationists and young Earth creationists are really on the same team, or the old Earth ID proponents like Michael Behe. Evolutionary theory, I think, has collapsed, and you know, if people really want to challenge me on that, you're welcome to. And I'll, you know, if they want to pose a challenge, I'll start right off with eukaryotic evolution, or the evolution of chromatin. or any number of membrane-bound organelles, or the major protein families. So even if we assume common descent, from a mechanistic standpoint, if we take cellular biology, chemistry, physics, statistics, evolutionary theory just doesn't add up. And it's even worse for abiogenesis theory. For that reason, I'm at least an old Earth creationist. That's where I was for a long time. What led me to Young Earth Creationism was the study, actually, of cosmology and solar system evolution. The nucleosynthesis of elements is not trivial. There are some theories that provide it. There's still problems with abundances, but some of the more down-to-earth, closer to home problems involve how do we get a nebula to evolve to be the planets that we have in the solar system. I read a book written specifically to criticize creationism, and it put forward how the solar system evolved, but on almost every other chapter, it was talking about this is a serious unsolved problem, and I'm like, yeah, no kidding. And there's no reason to expect it's ever going to be solved. Basic things like problems with angular momentum. Where did it come from? You know, when things are coming together because of gravitational attraction, they don't automatically spin. There has to be a little angular momentum to begin with. And then, yeah, when it spins, you might get a disk. But how do the disks become planets that are on different orbital planes? How about the differentiated chemistries? So I began to be very deeply skeptical of this. I said, you know, this is looking more like it's specially created, and especially created to resist evolutionary interpretations for those willing to look meticulously at it. But it's not so blatantly obvious that you'll find it unless you're willing to really carefully weigh the evidence. That's also the case with things like evolutionary theory and even abiogenesis. Superficially, it may look that it can come about naturally, but on closer scrutiny, it falls apart. Just today, for example, as I've been reading my textbooks on general relativity and studying physics, I was thinking, I think general relativity may have some problems. It even said so in my textbook. And Bernard Schurz's Introduction to Relativity. And here it was, I heard on Sabine Hossenfelder's channel, the back reaction. She's a respected mathematical physicist. She said, yeah, you know, general relativity could be wrong. People are trying to fix it with things like quantum gravity. I'm just like, well, yeah. I mean, it was in my textbook, but it's not well advertised. And you can look this up on Wikipedia. There is something we know that is called the time problem. And quantum mechanics really likes absolute clocks. And I've been thinking, yeah, you know, absolute clocks kind of put a wrinkle in everything as far as what we think about time, et cetera, and absolute coordinates. So those were some of the reasons I started to entertain Young Earth Creationism. But then this whole thing about genetic deterioration. No major geneticist thinks the human genome's improving. One geneticist by the name of Kondrashov said, why aren't we dead 100 times over? I'm like, yeah, you know, individually we have like an expiration date. Our genomes deteriorate in our somatic cells. We age. It is now becoming evident that the genome of the human species is probably aging too. It has an expiration date. And that is a testable hypothesis, sadly. If that is the case, it is unlikely that we evolved. And so the dividing line, as far as I'm concerned, is between young Earth creationism and old Earth creationism. If there's old Earth creationism, there would have to be miracles along the way. They would interpret the fossil record as showing a progression from various creatures to another, and there would have to be miraculous transitions along the way. And I pointed out one of them is the formation of membrane-bound organelles in eukaryotes. And I've shown videos of all those machines and things moving in and out of the cellular nucleus, and people, they're like, wow. I'm just like, well, yeah, that's pretty hard to evolve. If you didn't have, for starts, the eukaryotic cell would be dead. So that would be an example of where miracles have to be kind of sprinkled along the way throughout geological history. One way to have maybe a more coherent view is maybe to explore the possibility that the Earth, or the fossil record at least, or at least humanity, is young. And there are some physical considerations. People have claimed there's one thing called the faint young sun paradox. And when I put that on the table, what the other side will do is just reflexively Google and grab the latest article that they have. But they never read it carefully enough to see that there are problems with the model, the solutions that are proposed, not to mention just about every model that claims to have solved the faint young sun paradox, which means that the Earth should be an ice ball. It needed some form of greenhouse global warming to keep it warm enough as the sun evolved from a cooler star to a hotter one. It would have to be a miraculous, finely tuned global warming. And that's just one problem. The other things are like the Earth's magnetic field, some very excellent high, large power engineers like Russell Humphreys. He worked for General Electric, and that was his field, electromagnetism. He examined problems with things like the dynamo model of how the Earth's magnetic field is generated. This leads to a testable prediction of young Earth creationism, by the way, that there should be decaying magnetic fields. I mean, if hypothetically the human race and civilization last another 10,000 years, we should start to see continued extinction of the Earth's magnetic field. Now, granted, I'm expecting that we won't be around, but at least it is a testable prediction. Another testable prediction is the decay of the human genome. So that being said, I'll say that intelligent design, problems with abiogenesis theory, problems with eukaryotic evolution and other forms of evolution argue very much for special creation. I'll just throw that. I'm quite confident defending that. The problems, the problems with like flood geology, the problem of radioactive isotopes, the proportions of parent and daughter products is still very, very problematic. And you won't hear that in some of the popular creationist materials, but you will hear it discussed among young Earth creation researchers. And some of the proposed mechanisms I've disagreed with, and even a minority of young Earth creationists have disagreed with, such as the mechanism of accelerated nuclear decay. I should qualify that it's specifically isotropic accelerated nuclear decay, where nuclear decay across the whole universe suddenly, for no explained reason, accelerates. There's problems with that, and the other side has been very keen to point that out, and even a minority of young Earth creationists. So what this show is tonight is talking about nucleosynthesis and transmutation. Nucleosynthesis is how we are able to take various atoms and smash them together, make new ones, usually going from smaller atoms to bigger atoms, or parts of them. So the story goes, this happens in stars, and then the stars explode, and they release a lot of these elements that make our solar system. Transmutation means, well, you could just change one atom to another by various means. There's natural transmutation in what we call radioactive decay, where one element will just spontaneously change. It'll emit radiation, and you get another element. But there are other ways to change to change atoms, and one of them is what I call the photonuclear process. And that was discovered. Actually, I don't call it that. I don't call it that. It's the mainstream that calls it that. Lightning, for example, can change atoms, and that began to hearten the possibility that when we look at the proportion of supposed parent and daughter products that give us the ages of, like, say, rocks, maybe a different explanation than radioactive decay is the explanation for why it has that proportion. That proportion is used to assign a date to it. And I've tried to tell Young Earth Creationists, it's still not the best thing just to take some examples where the dating method definitely looks unreliable or fudged, okay? And not that it's, I shouldn't say intentionally fudged, but it's like, well, there are examples where it doesn't agree with what we know. Like, for example, if a rock we just saw form, and we know that it's not 200,000 years old because it formed under our eyes, and it's being dated that way. It's like, okay, there could be, problems with, how the daughter products ended up, the supposed daughter products ended up altering the proportions. But there are definitely cases that are problematic for Young Earth Creationists. And the reason I know this is I've been at some of their conferences, and they've said we don't have mechanisms to explain some of these. So tonight, I'm just going to try to explore some of the possible mechanisms that may cause this. And I've said that an anomaly that is very bad, is very difficult for the old Earth creationists, is the fact that there's 70 times more uranium in the continental crust than there is on the seafloor. How did that happen? And as I've read the literature on how the Earth supposedly evolved, we would have to have late sprinkling of uranium. That just looks awfully ad hoc and fortuitous, but still even worse is the 70 times proportion, 70 times more on the continental crust. So we might have even just a purely secular reason to explore reasons for the emergence of this. How would that be generated? Well, for those of us who are interested in Noah's flood, we would suppose that tectonic interactions could create enough electricity to start changing nuclear structure, but we're not out of the woods yet. That being said, we have recently, and a creationist by the name of Walter Brown foresaw this a long time ago, it's starting to become mainstream, that when we see earthquakes happen, there have been also simultaneously earthquake lights. And there are two mechanisms that may generate electricity to create these lightning storms or earthquake lights associated with earthquakes. One of them is the piezoelectric effect, where you have compression of rocks, it will generate electricity. That's known. You get that example with your butane lighter, for example. When you're clicking it, you're compressing a rock and making electricity. Another is the triboelectric effect. So on a dry winter day, as you move around, you start, probably touching the carpet or whatever, the floor. The friction starts to contribute to you developing an electrical charge. You touch the doorknob, you release 30,000 volts. You release an arc of 30,000 volts. Yeah, it's pretty hefty. And that's an example of the charge. The reason it doesn't kill you, the voltage, crudely speaking, is a measure of the quality of, the quality of the electrons, the potential energy that is being released into kinetic energy. It lacks the quantity. if it had the quantity, like say, of your electric currents that power your 100-watt light bulb, you'd probably be dead. So that's the reason, even though it's 30,000 volts, it doesn't kill you. But on large scale, we have things like, you can imagine it'll generate a lot of electricity, probably in the millions of volts. That's, I'm just speculating here, but it could. One reason for that is we have things like the Van de Graaff generator that basically takes rubber and rubs it against a metal sphere, and you get up to 5 megavolts in some of these Van de Graaff generators, and that uses the triboelectric effect. There are other electric effects like pyroelectric and flexoelectric. I only know those in passing, so I can't comment on those. So there are reasons that we can expect tectonic action can generate electricity, but we're still not out of the woods. But it's a start. It's a start. When I started to hear lightning bolts can generate neutrons, I began to be heartened, and I will review some of the experiments that relate to to electricity generating transmutations. Now, I've been putting out papers where more and more experiments are happening where we're able to do transmutations in mixed energy environments. That is, you may have one block of mass in the solid state rather than the plasma state. And then you take something in the quote unquote hot state and you interact them, you can change it. That's almost good enough for now, for what we want, for young Earth creationism to at least start to have a glimmer of hope that we can change the elements. But there continues to be this question of really, truly low energy changes. Now, we definitely know of one avenue where we can have low energy changes. It's called muon catalyzed fusion. One of the people who worked on muon catalyzed fusion was Stephen Jones. He was one of the pioneers. He set the record for how many deuterium fusion reactions you can get per muon. He set the record. So he was a respected researcher in this. And I want to show a headline. Let me see if I could find the headline. S.E. Jones. And I'm going to show it here. This is a forgotten article. And let me show it here. Let me do a little cleanup here on some of my on my panel here, on my control panel. Just, give me a moment, please. It's a good time for me just to take a little pause. And I need to put this in the video description, by the way. So in the prestigious scientific journal Nature, 1989, it says here, observation of cold nuclear fusion in condensed matter. Cold nuclear fusion in condensed matter. So again, I'd like to emphasize he was a recognized researcher in some of the first cold fusion experiments, ones that have actually been accepted by the mainstream, mainly muon catalyzed fusion. He got away with getting this thing published in Nature, but because of the controversy with Pons and Fleischmann, the very acknowledged difficulty in repeating these experiments, and sadly a lot of cranks and charlatans getting involved in the mix, the whole idea got into severe disrepute, some of it deservedly so. But Stephen Jones did have at least a lot of the right experimental techniques to confirm whether reactions have happened. I've read some of his papers where he goes into detail of all the instrumentation. So all of his lab instrumentation that he used to do the muon catalyzed fusion, he can apply to the cold fusion stuff. He certainly had the expertise. And so the reason I throw that name out is that's one example of credibility. That it may have a chance of being true. The other one would be Julian Schwinger, who won the Nobel Prize along with Richard Feynman on quantum electrodynamics. And that's a whole nother set of drama where he started to publish this and they shut him down. And just like, you don't shut down someone who won the Nobel Prize in physics. He could sit on a peer-reviewed committee. What was that about? And it's really sad is because then you do have people like Stephen Jones who actually did accomplish cold fusion in his experiments, and that was accepted. So what does it take to accomplish cold fusion? And this is something I want to again acknowledge Mr. Jetty 89, who's a frequent commenter on this channel. And I got to tell you something about Mr. Jetty. The more I know about him, the more my jaw drops as far as how smart and educated he is. He's very smart, very educated. I'm just like, I'm so honored that he would be in the audience to hear me, because my knowledge base is so small compared to his. He works on an accelerator. I mean, I'm so privileged to have someone of his caliber listening in on this and critiquing me and humbling me. I mean, that's a little painful, but these are some things I got to think about. And so one of the problems is, let me just back up a little bit. The problem in fusion overall is what we call the Coulomb barrier. You see it here. And that means when you have two positive charges, when you try to bring them together, it takes a lot of force or energy. Okay, so for the formalists out there, change in a momentum is equal to the force. And so if you have something that's moving along real fast, two nuclei coming along together real fast, you can effectively, it's almost like forcing them together, okay? So they start to decelerate, but their change of momentum is kind of equivalent to a force. And so you just need to get the two bodies to be coming at each other fast enough, having enough relative speed. And that will be defined by this equation here. And what I realized is, okay, it's not too bad when you just have like hydrogen or heavy hydrogen nuclei that only have one positive charge each. It's not too bad. I mean, it's bad enough that you would need an atomic bomb to set this off, to get enough temperature and heat the system up, and then these things start to collide and they could start to fuse and then release energy. And I think I had a diagram of an atomic bomb. Do I have it? The diagram of an atomic bomb. If any of you recall, it starts with a chemical explosion here in the green that forces the uranium to come close together. The uranium then will start to fission and make lots of heat, and it gets here into the deuterium, and it warms it up. When it's warm enough, then we can overcome the Coulomb barrier, and we make a thermonuclear explosion. But can we do this at low energy? So the thing that's been proposed is, what if you can just put a negative charge there, or an equivalent negative charge there? You can zero this out and you can get fusion at low energy. So let me just suggest some things, and this is where my quantum mechanics isn't all that good. First off, I already said muons are one way, but they're big, heavy particles. They're negative. You get them so that they can do what they call screening. They just have to be positioned in the right way so that you can at least reduce this. You can get this to happen at lower temperature. Now, if you can get an electron here, you can also do the same, but that's kind of tricky. So what they have suggested is, in a condensed matter state, you can look this up on Wikipedia. They call it quasi-electrons. You might be able to use heavy quasi-electrons, there are all these quasi-particles you could make, and maybe you could negate it, or what they call just kind of the electron screening in the lattice. This is some tough quantum mechanics, and it's why they call the field of solid state physics squalid state physics, because you get lots of these quasi-particles. They're not real particles, but they're almost like the real thing. You can model it. So for the electrical engineers out there, you hear about electrons, electron holes. In biology, there's lots of quasi-particles, one of them being the exciton, and there are other quasi-particles like plasmons, magnons, polarons, and of course the quasi-electron, the heavy electron. So these have been some things that have been bumped around. Now I will point out that there was this, as far as electrons getting into the nucleus, again, this is a quantum mechanical thing, why it doesn't fall into there. I will point out, there is an article that covers it. You know, ask the question, why don't electrons in the atom enter the nucleus? And this is one thing that has kind of like, well, you know, when you take physics classes, they talk about Schrodinger's equation and the discrete energy orbitals in the Bohr atom, and they try to explain it to you, but it's like, okay, why doesn't still you have like a negative electron and then a positive electron that they call the positron antimatter. They seem to be able to come together. Why doesn't the electron spontaneously do that? And so that's always kind of like, I've never figured that out. But there is a situation, let me see if I could find it. So in nanotechnology, let me just read this. I'm going to mess it up if I try to summarize it. Long predicted atomic collapse state observed in graphene. Okay, researchers recreate elusive phenomenon with artificial nuclei. So this is theoretical. This was Mr. Jetty 89 pointed out, this wasn't absolute proof of it, but it was, we tried to simulate it, and it is a theoretical prediction. The first experimental observation of a quantum mechanical phenomenon that was predicted nearly 70 years ago holds important implications for the future of graphene-based electronic devices. Working with microscopic artificial atomic nuclei fabricated on graphene, a collaboration of researchers led by scientists of the U.S. Department of Energy's Lawrence Berkeley National Laboratory and the University of California, Berkeley have imaged an atomic collapse states theorized to occur in super large atomic nuclei. Atomic collapse is one of the holy grails of graphene research, as well as the holy grail of atomic nuclear physics. I'm going to keep going on here. Let me see. Originating from the ideas of quantum mechanics pioneer Paul Dirac, atomic collapse theory holds that when the positive electrical charge of a super heavy atomic nucleus surpasses a critical threshold, the resulting strong Coulomb field causes a negatively charged electron to populate a state where the electron spirals down to the nucleus and then spirals away again, emitting a positron in the process. This highly unusual electronic state is a significant departure from what happens in a typical atom, where electrons occupy stable circular orbits around the nucleus. So that's about all I'm going to cover on that. This is obviously starting to get way over my head, but there is a situation, in other words, where I was trying to head, where you can get the electron into the nucleus, albeit briefly. All right, so we may be going into territory where we're going to just talk about it. I'm just going to review experiments and say we don't know how this could happen. So bear in mind that, you know, it's difficult to get a fusion reaction. It's hard enough to make a fusion reaction with hydrogen versus hydrogen. I'm now going to start. You can imagine that as we get higher atomic numbers where the charge is bigger, this is going to grow by order z squared, meaning when it's bad enough when you just have one charge versus one charge, one positive charge versus one positive charge. You get to copper where it's 29 charges versus 29. That's 29 squared. The problem has gotten bigger. And I'm going to cite experiments where it's claimed that this is somehow overcome by effectively getting the electrons to reduce the Coulomb barrier. All right. So right. The one Jordan here points out, that's spawn quantum mechanics. The one that really still perplexes me, and I don't have any particle physics here, is the electron and positron. How do they come together to annihilate each other? Because, so I'm just leaving it at that. So anyway, let me now try to, I have to go gather my documents here. So if you'll indulge me. So in my infamous graduate paper in 2012, I began to explore the question of, okay, can we at least get transmutations? So there was a contested issue over whether tungsten could be transmuted. So Ernst Rutherford, who's famous for his alpha particle experiments, that we realized that the nucleus and the electrons are separated by a lot of space. He had Geiger there shooting alpha particles at gold, and some of the particles would shoot right back, and that astonished everyone. And he said, okay, that means the nucleus is very dense. When it hits that, it bounces back. He won the Nobel Prize in chemistry, ironically not in physics, but in chemistry for that. He might as well have won it in physics because that was a big deal. It's not well known that he was also a pioneer of hot fusion. Oliphant and one other researcher did an experiment, published a paper on where they were able to fuse hydrogen. So he was a big deal in that. So very respected. So there was an experiment by Wendt and Irion that was published in the prestigious journal Science. And Rutherford came out in the prestigious scientific journal Nature and criticized it. And I'm just going to read some of this. But it seems to have, from what we know about these experiments, they're called exploding wire experiments, where you take electricity, run it through a wire, and just make it explode. So Wendt and Irion claimed that they were able to get they were able to transmute tungsten to something else. Not all the tungsten, but some of it. And Rutherford said that couldn't happen. Well, in the 2000s and even in the 1970s, they began to redo the exploding wire experiments. Unfortunately, they involved deuterium, but they still had wires. They'd pump electricity through it, and they would get transmutation. They get indications of neutrons or gamma rays. So let me just read through this. This article by Alan Wydum and someone named L. Larson, I think they extrapolate, they're trying to promote their cold fusion theory, which I think is largely discredited now. I was neutral about it in 2012. I'm very negative on it now. But they were my first introduction that actually started looking at experimental evidence. So I'm going to try to read it. I'll comment where I totally disagree, when I think they're off base. But the important thing is they'll be discussing the experiments. This will then start kind of be a stepping stone to Adamenko's experiments in the Ukraine. So energetic electrons in nuclear transmutation and exploding wires. Nuclear transmutations and fast neutrons have been observed to emerge from large electrical current pulses passing through wire filaments, which are induced to explode. The nuclear reactions may be explained as inverse beta transitions of energetic electrons absorbed either directly by single protons in hydrogen or by photons embedded in other more massive nuclei. Okay, that second sentence has been hotly contested, and I think it's wrong. Okay, so I'm just throwing that out there, but I'll continue with the paper. I just want to acknowledge that I'm not in agreement with that. The critical energy transformations to the electrons from electromagnetic field and from electrons to the nuclei are best understood in terms of coherent collective motions of many flowing electrons within a wire filament. Energy transformation mechanisms have thus been found which settle a theoretical paradox in low energy nuclear reactions, which has remained unresolved for over 8 decades. It is presently clear that nuclear transmutations can occur under a much wider range of physical conditions than was heretofore thought possible. That I agree with. As I said, the photonuclear processes are coming into our consciousness now on this. Over 80 years ago, Wendt and Irion reported nuclear reactions in exploding wires, and that was in the journal Science. The transmuted nuclear products emerged after a large current pulse was passed through a tungsten wire filament which exploded. Sir Ernst Rutherford expressed doubts as to whether the electrons flowing through the wire could carry enough energy to induce nuclear reactions. The exploding wire current pulse had been produced by a capacitor discharge with an initial voltage of only 30 kilovolts. Okay. And as I said, 30 kilovolts, okay, I hear this figure a lot. Your static discharge on a cold winter, dry day, 30 kilovolts. Going on. On the other hand, Rutherford had employed a high energy but dilute beam of 100 kilo electron volts electrons fired into a tungsten target. Rutherford did not observe any nuclear reactions. Wendt replied to the Rutherford objections, asserting that the peak power in the exploding wire current pulse was much larger than the relatively small power input to Rutherford's electron beam. Most importantly, a large energy transfer from the many electrons in the wire to the nuclei could occur collectively, which would allow for the nuclear transformation energy. Let me comment here. This is like focusing. You have a magnifying glass. You could use the same energy depending on how tightly you focus it will determine whether it could start a fire or not. I don't think that that section was worded well when they talk about a diluted beam. You want to have a very high electron density to get this going. Subsequent experiments have seemed to bear this out. You need a high, and Adamenko's paper will actually cover the importance of electron density, basically the coulombs per cubic meter or cubic centimeter or whatever. Very old but important debate between Wendt and Rutherford has presently been experimentally set in favor of Wendt. That's qualified. Not the specific tungsten experiment, tungsten only experiment. So Wendt was tungsten only. It has been confirmed with deuterated wires or wires that have some sort of deuterium environment. It does work there. So that's not exactly right, but I'm just going to move forward here. The more recent exploding wire experiments have, beyond doubt, detected fast emerging neutrons capable of inducing nuclear transmutations. These observed fast neutrons have often been attributed to the products of deuteron fusion, but we find that hypothesis unlikely to be true. First, fast neutrons have been seen in exploding wires, even though there were no deuterons initially present. I don't know how he got that. I looked at the references 4 and 5. Okay, so I'll go on. Secondly, I may have to revisit that. That would be interesting. Secondly, the gamma emission signature of deuterium fusion has not been observed. Now that is interesting. That's an interesting part. We see fast neutrons and no gamma emissions. That's interesting. It is much more likely that the fast neutrons are products of inverse beta transitions, again, controversial, of very energetic electrons absorbed by protons and producing fast neutrons and neutrinos. Okay. So just caveat emptor here, don't believe everything you're reading. I'm just throwing this out. The protons may be hydrogen atomic nuclei, or protons may be embedded with more massive nuclei. The theoretical side of the difference of opinion between Wendt and Rutherford concerning how large amounts of energy can be transferred to and from the electrons in the wire has remained unresolved. The purpose of this work is to explain how this collective energy transfer may occur. Okay, so unfortunately, this is where we get the theoretical stuff of Wigham and Larson, rather than just reviewing the experiments. The reader has perhaps unwittingly observed exploding tungsten wire filaments in household light bulbs. Now that's interesting. Normally the hot wire glows in the yellow optical frequency, slowly evaporating metal atoms from the filament. Over time, the wire filament thins in some pinch regions, strongly increasing the Maxwell magnetic pressure. Then with a pop, the filament explodes, shifting the final bright radiation pulse frequency upward into the blue. The filament is broken at the pinch points. The reader may have shaken the bulb and heard the broken metallic pieces of filament rattle from within the bulb, or noted the explosion dust on the inside surface of the bulb before replacing the old light bulb with a new one. Now let us consider this process only at much higher currents, temperatures, pressures, and energies. And this is kind of the sad thing now that they described the Wendt-Irion experiment. It's, we're moving away from the tungsten light bulb. Oh well. The scale of wire currents required to induce nuclear reactions may be found by expressing the rest energy of the electron mc squared in units of current I naught by employing the vacuum impedance RVAC. Oh, that's interesting. Vacuum impedance. One finds, and he's going to work that out, that I0 is 1.7 times 10 to the 4th amperes. If a strong current pulse, large on the scale of I0, passes through the thin wire filament, then the magnetic field exerts a very large Maxwell pressure on the surface area elements, compressing, twisting, and pushing into the wire. If the magnetic Maxwell pressure grows beyond the tensile strength of the wire material at the hot filament temperature, then the wire begins to melt and disintegrate. If the heating rate is sufficiently fast, then the hot wire may emit thermal radiation at very high noise temperature. The thermal radiation for exploding tungsten filaments exhibits X-ray frequencies indicating high electron kinetic energies within the filament. Due to the electron kinetic pressure, the wire diameter starts to increase, yielding a filament dense gas phase, but still with some liquid droplets. The final explosive product consists of a hot plasma colloid containing some small dust particles of the original wire material. These products cool off into a gas and some smoke, as is usual for explosion. In order to understand how the electrons are accelerated into high energy regimes, recall that a very rapidly changing current induces a Faraday law voltage across an inductive circuit element. And I know Ben Rex, you're loving this, our resident electrical engineer. The Faraday law voltage per unit length E is determined by the self-inductance per unit length. And I'm not going to read all that. Boy, this is bringing back memories of electrical engineering where they talk about self-inductance. So I'm just going to move forward. I think it's important that we just, as you hear the details of the experiment and some of the examination, it just kind of strengthens the credibility of this. Dimensionless geometric factor eta for the inductance per unit length also varies very slowly with the wire cross-section area A naught. And I'm just going to skip some, and people who want to read this can, but I wanted to at least read some of this. This is really good physics, electromagnetic theory, electrical engineering. All right, so a charge in the collective current Di yields a changing electron momentum and thereby a change in the single electron energy dW, wherein V is the velocity of that electron. The single electron energy can thereby reach values far above the electron rest energy for pulse peak current large on the scale of I naught. And I naught again is, calculated it here, 1.7 times 10 to the fourth amperes. That's what, 17,000 amperes? Wow, yikes, 17,000 amperes. And he'll argue that is sufficient to cause a nuclear reaction. So now, as I've covered, as I went through the references, when I wrote my graduate paper in 2012, I actually looked up those experiments. They were in plasma physics papers. And yeah, they were detecting neutrons and all sorts of things that you would expect in a nuclear reaction. So nowadays, using electricity to generate neutrons is kind of passé. There are devices like chemists can use if they want to make isotopes. You just flick the switch on, it's going to make neutrons. That's pretty cool. You could, there's a device on it. You can look it up if you want to make a neutron generator. So, I mean, it's kind of passé now that we can make neutrons with electricity. Numerous experiments. The important thing I'm trying to point out is there's a wider range than, you know, maybe even students of physics like myself would have thought, where we could create nuclear reactions. There's a wider range of things available to us. So now let me go on to Adamenko's paper. Adamenko is in the Ukraine, and so are his colleagues, Vostosky and Adamenko. Vostosky has worked with people in Moscow. So this is really sad, this war going on in Ukraine. I heard that half the soldiers in the Russian army have family in Ukraine. And anyway, for the sake of science, I hope this progresses. I read in the, let me describe these scientists here, and it's going to be connected to scientists here in the United States, one of whom I actually was hoping to go to his school to get my PhD in physics, and that would be George Miley, who was at the University of Illinois, Urbana-Champaign, because he's very friendly to the work in the Ukraine. He co-authored some of the papers in Ukraine. And my jaw began to drop when I saw the qualifications of the people both in Ukraine and in the United States that are working on this project, and also at the Oak Ridge near the Oak Ridge National Laboratory. These guys are physicists. So there is kind of a little cottage industry of quote unquote misfits, rebels, that seem to be highly qualified scientists that are advocating alternative means of changing nuclear structure, particularly involving electricity. So let me see if I can call up some of these papers, if you'll indulge me here. So I put some links in the video description. Here's one where we can use lasers to change nuclear structure. Let me show this one. We now have lasers doing this. This article's Nature Communications, generating kilo-electron ion distributions from nuclear reactions at near solid density using intense short pulse lasers. And you read this. Now, this isn't electricity directly, but it gives some insights. They have a particular catchphrase that really caught my, the section here that really caught my interest. It says here, nuclear reactivities are dominated by the Coulomb barrier. Nuclear reactivities that are dominated by the Coulomb barrier will be drastically altered by the presence of non-thermal multi-kilo electron volt tails in the ion distribution. Let me read that again. Nuclear reactivities that are dominated by the Coulomb barrier will be drastically altered by the presence of non-thermal multi-kilo electron volt tails in the ion distribution. Okay, nuclear reactivities. Okay, what this is saying is the problem with trying to make fusion going from hot to cold is the Coulomb barrier. That Coulomb barrier can be altered by the presence of electrons or ions, drastically altered. So I'm just pointing that out. This is like a 2018 paper in Nature Communications. So I mean, I got to tell you guys, this stuff 20 years ago, there was none of this. I mean, this would be thought of absurd. I mean, if you got the sentiment 30 years ago during the Pons and Fleischmann, it's like, this is definitely crank. But, you know, it's starting to become mainstream where we can take ions and electrons, high concentration, start altering the Coulomb barrier, which means getting the fusion to happen at colder and colder temperatures. All right. So again, the idea is you have the earthquakes, the tectonic activity, generate electricity. The electricity may create these high densities of ions or electrons. The electrons can then, hopefully, for the young Earth creationists, if you are, start to alter the Coulomb barrier so that nuclei can fuse. Now we have nucleosynthesis. So let me now go to some of Adamenko's paper, and I know this is going to be painful. I'm going to read the easier paper by Adamenko. I was planning to read the harder one. This is, you know, there's torture enough. So let me read this. Now, let me give some background and who the players are. First read the list of authors. S. Adamenko, that's the chief, Stanislav Adamenko from the Ukraine. He works in the, okay, he's one. George Miley at University of Illinois Urbana-Champaign. He's a researcher, professor, Department of Nuclear Plasma and Radiological Engineering. All right, so he's knowledgeable in this area. I don't see Vostoyski's name in there, but Adamenko had worked with Vostoyski. I'll just mention who Vostoyski is. He is head of the Department of Mathematics and Theoretical Radiophysics at Taras Shevchenko National University, Kiev, Ukraine. And by the way, I hope he's okay. There is Dmitry Nonikov. All right, I'm going to give you the LinkedIn entry of Dmitry Nonikov. I just want to read his qualifications. Now, you know, this is a little bit of argument from authority, but at least I'm just trying to say these guys these aren't just random used car salesmen that were grabbed off the street to make these assertions. Okay, so I'll read a little bit about him. see if I can make this bigger. Currently consulting on private fusion energy sector. Until last year, managed Proton Scientific Incorporated, 2012 to 2021, Champaign, Illinois, and Oak Ridge, Tennessee. First DOE, Department of Energy, Infuse Grant awardee in 2019. Fusion-powered research and development project with 5 to 10 physicists and engineers. $7 million in private equity funding, developing theory and hardware in collaboration with Voss Scientific and Alpha Omega Power Technologies, using the company's Thunderbird intermediate level, that's 0.6 megavolt, 600 kiloamperes. Okay, so we got to that figure that was cited by Whiteham at 17,000 amperes. We have one at 600,000 amperes. 600,000. 20 gigawatts. Pulse power device as well as pulse power facilities of collaborators. Now that Thunderbird device is basically the one that was, it's a improvement of the one that was in the Ukraine. And we're going to talk about that. I'm going to cover that, okay? So just remember this device and the numbers. Pulse power facilities of collaborators. Fusion pulse power experimental scaled up device to demonstrate the energy break-even was designed with an estimated cost under 20 million. Compared to the 3.5 billion laser device at the National Ignition Facility currently in use in pursuit of the same goal to reach energy break-even level fusion reactions. Okay, so just for those who don't know, there's green energy, and then we want to have, it's desirable to have fusion energy. It'll be cleaner than your fission reactor, your normal ones, your regular fission reaction electricity. There are a lot of other benefits. So, and plus it's just really cool. So the reason that there's money being, your taxpayer dollars are funding this, okay? That there's interest in this is because of being able to have clean energy that's not this renewable green stuff. It's better than that. You know, some of these renewables aren't really renewable. They cause a lot of pollution along the way anyway, and it doesn't do what you want to do. Plus, NASA is interested in this to power spacecraft. So I'll go on. The electron beam fusion device is expected to be the most economical fusion energy generator in the inertial confinement fusion category, with the ignition pulse power driver technology applicable to commercial power production. Okay, so this is the part where, okay, this is the hype of, you know, what I call dream energy. Transmutation is of interest to YECs. Whether you can, we know we can make fusion reactions with electricity. Okay, that's like without any doubt. It's whether you can make an actual energy reactor that can do this. This is where the crankdom can be. Okay, so I'm not going to endorse that this will actually lead to a fusion reaction. I mean reactor. What do they call it? Excess heat, where you get more energy out of the system than you put in. We definitely have fusion reactions where you put way more energy into the system than you get out of the reaction. That's the one that the Young Earth Creationists are more interested in. So unfortunately, this is where some inflated claims, hustling for grants and money and prestige can get in the way of the actual science. And that's just too bad, because there are some legitimate experiments, okay? I've tried to highlight all the experiments in well-accepted peer-reviewed literature that says, okay, we can do this. And there, you know, as I said, there are devices now you could, I wouldn't say you could exactly buy it off Amazon, but you just flip an electrical switch, it's going to make neutrons for you. So there's definitely ways you can do this. All right. As far as whether it's going to solve our energy problems and alleviate all the problems associated with tyrants controlling natural resources, that's you know, that's not what I'm specifically interested in. But anyway, I'll go on. So He was the research assistant professor of the Advanced Imaging Center at IG5B of the University of Chicago and the Argonne National Laboratory, the director of MCB Imaging Facility, University of Illinois, and he had original work in analytical microscopy applications in the featured Nature Methods Journal and Nature Milestones, DNA Technology, and specialty textbooks including MBOC by Alberts et al. 5th edition and current 6th edition. Now that's actually close to home because I studied, when he mentioned Alberts, Alberts wrote Molecular Biology of the Cell and also Essential Cell Biology. I have the 5th edition. So it's funny how you'll have people that have physics specialties being involved in biology. That's what I said. The people that advance things in biology are the physicists, engineers, not the evolutionary biologists. Okay, sorry. I know that's harsh. But it's been my experience, the research teams, the technologies that enable us to understand how biology works, they're by and large not done by evolutionary biologists. They're done by physicists, engineers, mathematicians, computer scientists, chemists especially. And so he's obviously had a great background. I could read about George Miley. So these are guys on the United States side that were collaborating with the Ukraine laboratory. So what did the Ukraine laboratory do? Now I'm going to cover that before I cover the theory. Let me try to, and I'm sorry this is long-winded. I said this is going to be a nerd torture session because I'm trying to be thorough and just highlight, try to make the case that there are some things that need to be looked at again. And I'm actually surprised only a minority of young Earth creationists are involved in this. So let me see. Okay, before I go there, I'm going to introduce George Miley. I promise I'll get to that. Papers by Adamenko. George Miley, he is mentioned here, and I'm sorry for the smallness of the text. Notice the journal here. It's the American Physical Society. That is the premier physical society in the United States. Thousands of members. If you publish in this journal, you've got mainstream recognition. So one of those is George Miley, and he talks about dynamics of superpinch electron beam and fusion energy perspective. Okay, well recognized here. I'm just pointing that out. And also, who else is named here in there? Dmitry Novikov and Miley. So they are recognized mainstream scientists. So this is mainstream work, this part. You might complain about their other stuff, but you can't say that they are totally out of the mainstream. They're definitely recognized. So now let me see if I could find the article I really want to cover. So let me kill this. I'll kill this window. And I'll kill this window. This is it. All right, I'm going to read through this now. One of the most fundamental processes in the universe, the nucleosynthesis of elements, its energy production in stars, as well as the creation of all atoms heavier than hydrogen. To harness this process and open new ways for energy production, we must recreate some of the extreme conditions in which it occurs. We present results of experiments using a pulsed power facility to induce collective nuclear interactions producing stable nuclei of virtually every element in the periodic table. That's a big claim and true. That's fabulous. Good news for young Earth creationists. A high-power electron beam pulse striking a small metallic target is used to create the extreme dynamic environment. Material analysis studies detect an anomalously high presence of new chemical elements in the remnants of the exploded target, supporting theoretical conjectures of the experiment. These results provide strong motivation to continue our research, looking for additional proofs that heavy element nucleosynthesis is possible in pulsed power laboratory. So let me go back a little bit. So I highlighted the current, the calculations for the amount of current, the amperes, in the exploding wire experiment that will cause nuclear reactions. So you could send these electrons going through through a wire, or you could just make an electron beam and strike a target. You could. The thing is to have the thing is to have the focus of the electrons to have a high density per cubic meter. Okay, high density of electrons in one location. There's a question here about how is this different from Z-pinch? The Z-pinch involves a wire. So as the electricity goes through the wire, it pinches. As they said, you could see the little pinch points when your light bulb blows up. That's if you have a tungsten wire light bulb. You had little pinch points. That's just caused by you need a little electromagnetic theory to talk about why it pinches. It gets kind of severs itself. In this case, it's an electron beam without a wire when it's just flying through space, presumably through a background. Okay, so these are pretty big claims here that they can get all elements of the periodic table plus an overabundance of heavies. You would definitely, almost definitely, you would have to you'd have to figure a way to get around your ordinary Coulomb barriers, and they are claiming basically that the electronic configuration, you're leveraging the high densities of electrons there and reducing the Coulomb barrier. That's the theory. The most important thing is whether their experiments are valid. Are they getting contamination or something? Or is it something else? We just don't know. Now, as I said, I tried to confirm, definitely there's transmutation when we have electricity. But can we transmute these sort of things? So the transmutations that I have talked about, and it, just as I was reading the Whitem paper there, references 4 and 5 on Whitem's paper that said it didn't begin with deuterium. That's news to me. So this is a big deal if we can actually do this without deuterium nuclei. The experiment I cited with the laser pulses, that's on plastic. That's on, I think, like plastic. They're laser pulsing plastic, and that's not. And I don't believe they use deuterium. They're causing nuclear reactions, transmutations there. And that's where I quoted, even in the video description, that the distribution of ions can drastically alter the Coulomb barrier. So okay, I'm just trying to throw this out there. We're going into territory that there's both a lot of crankdom, and then you have really elite scientists. We have some confirmed results. We have a lot of unconfirmed. Okay, so I'm just going to read through this. I just feel it's my responsibility to give you some caveats here. And Mr. Jetty 89 will definitely have his opinion. He works on an accelerator facility, and he's generally negative on the stuff I put forward. I believe he's an old Earth creationist, or at least the old Earth intelligent design proponent from his comments here. He's a devout Christian. So this is not between atheist and non-Christian. He's a Christian brother. We have disagreements, and this is a scientific discussion. I totally respect his opinion here. He's very knowledgeable on this, but I'm just gonna, okay, caveats thrown out there. I'm just gonna keep now plowing through the paper. Nuclear fusion processes that drive energy production in stars, as well as the creation of nuclei as heavy as iron and nickel, are understood well enough to start conceptual designs of new types of power plants to harness some of these processes. Fusion reactions in star interiors, as well as those in hot plasma generated in the laboratory environment, are based on mechanisms of pair collision in the reacting nuclei, where their kinetic energy is high enough to tunnel through the Coulomb barrier and engage in strong nuclear interactions. At the same time, even a theoretical concept of processes in the universe responsible for the production of nuclei heavier than iron and nickel is incomplete. Reference 5, 6, and 7. Like fusion models, current models of heavy element nucleosynthesis are based on pair collision mechanisms involving a capture of free neutrons by target nuclei, which then undergo beta minus decay, moving to higher atomic numbers in the periodic table. Relatively slow neutron capture is still called the S process and takes place in the stable interiors of massive several solar masses, stars, on timescales ranging from 10 million to a few billion years. But if we consider the isotope composition of the universe, the model of the S process alone can only explain the abundances of about half of the heavy isotopes. Creation of the remaining isotopes is generally attributed to other pair collision type processes, with the largest contribution by the rapid neutron capture, or the OR process, which is theorized to occur solely in type 2 core collapse supernova, references 6, 7, 8, and 10. On much shorter timescales of a few seconds, our process models of different levels of sophistication have been constructed over the years. Yet unanswered questions are by far more numerous than solved problems. Yet unanswered questions are by far more numerous than solved problems. And let me acknowledge people that just came in. Wesley Coleman and Bread of Life is back. I'm sorry about the funny microphone. Yeah. I know why that happens. It's when I scroll. Thank you very much for the feedback. So I'm gonna scroll things, wait a little bit, and then wait. Let me get this continues. Some answers to numerous unresolved issues in heavy element nucleosynthesis may be found in alternative theories and models. One of these models is the concept of collective nuclear interactions that suggest a nucleosynthesis mechanism occurring on a very short time scale. Okay. I'm going to wait just a little bit to stop the mic problems. Okay. According to this concept, collective nuclear interactions may be triggered by simultaneous acceleration of all particles in the system. If amplitude and coherency of the acceleration are high enough, these factors may significantly increase the transparency of Coulomb barrier. In this case, contrary to pair collisions, the strong interactions will be engaged not just between two reacting nuclei, but throughout large ensembles of nuclei, which will form heavy nuclear clusters as a result of system self-organization. Let me know if the mic is okay as I read the paper. In any finite volume, such coherent particle acceleration cannot be sustained indefinitely. Once the acceleration starts to drop, these heavy nuclear clusters become unstable and decay into various stable isotopes. Unlike pair collision nuclear reactions that are characterized by specific nuclear products, the nuclear transmutation process driven by the collective interactions produces stable isotopes of virtually every element on the periodic table. Most of the matter in the universe exists in a state of thermal equilibrium or quasi-equilibrium, which is signified by random particle acceleration. Shock waves that restore thermal equilibrium in the media cannot create conditions required for coherent particle acceleration for the same reason. This is really interesting. This is really interesting. They're basically saying that if you have very unusual circumstances, like a, you know, when you get accelerations of stuff, okay, so let's say you just suddenly have like a lightning strike, which could happen now because you have continental plate movements. When you get these accelerations of, you know, away from equilibrium, and it happens very quickly and suddenly, kind of what we call, like, say, a voltage spike, that may trigger this. So this is not a process that will normally happen in stars, you know, stable stars. The process they're describing has to have, you know, it has to be kind of explosive, for lack of a better word. Okay, so let's go on. Coherent acceleration, however, can be achieved by an action of a long-range force, which can be either gravitational or electromagnetic force. Electromagnetic force. In the former case, a possible site for such process is type 2 supernova during its core collapse, driven by strong gravitational field of the dying star. It is remarkable that this potential site for collective nuclear interaction process is very close in time and location with the site for your process. Electromagnetic force can also create an environment for coherent acceleration of ions. A radiative collapse of Z-pinch is one of the mechanisms that could serve this goal. Again, we have confirmed experiments of this, all right, accepted in the mainstream, beyond question at this point. A radiative collapse of Z-pinch is one of the mechanisms that could serve this goal. However, in our research, we utilize the effect of electron beam channel collapse induced by electron beam solid target interaction and beam self-focusing in the dense plasma of the resultant virtual electrodes. I'm going to pause here a little bit. This stuff about the electron beams and stuff, I cited the paper in the American Physical Society. It's very well respected, peer-reviewed. It was specifically about two of the co-authors. It was co-authored by Novikov and Miley. They worked on the electron beam. Okay, this is mainstream peer-reviewed in a premier journal. That part is correct. They're qualified to make these electron beam devices. They would know about all the details of this. They are co-authors on this paper that claims we can use those electron beams to synthesize other, to do transmutation, create all the elements in the periodic table. Create all the elements in the periodic table with electron beams. Okay, so one part is definitely within the mainstream, that is building electron beams. Another part is the Z-pinch. What is still doubted by my colleagues here on the internet and the general scientific community is whether you can create all these elements on the periodic table by using this device. So when I was reading Novikov's LinkedIn description, it talked about the Thunderbird device. Okay, this is describing some of the mechanics of this Thunderbird device that can make electrons at 600,000 electron volts at 600,000 amperes, 20 gigawatts. Okay, they're describing the Thunderbird device. Ben Rex and I could probably work through the numbers. It's actually interesting because I have a space heater here, 1400 watts. If you run it for 1 second, that's 1400 joules of energy. And surprisingly, when you hear all these big numbers, what they do is they're able to make the pulse in only like a few nanoseconds. So it works out that me running my space heater for about 1 second has the same energy that you're here described here, but the power and concentration is these gargantuan, monstrous numbers because it happens in such a short period of time. You're just getting this huge energy burst that happens in nanoseconds rather than over 1,000 seconds. So you're basically compressing, me running this for about 1 second by 1 billion times. So in this paper, we described a pulse power laboratory experiment to test the concept of collective nuclear interactions using high power nanosecond scale electron beam pulse striking a small metallic target. Nanoscale electron beam pulse striking a small target. Again, you just have a very short burst of energy, and that's how you're able to concentrate it, kind of like a magnifying glass. A material analysis study shows anomalously high concentrations of new chemical elements that are present in remnants of the exploded target. These elements are spread across the board of the periodic table and are detected in amounts consistent with energy balance estimations, assuming that they are formed from the original target material. Pulse power device and experimental setup. While a manipulation of gravitational field is unattainable in the laboratory, another type of long-range interaction due to electromagnetic force can be reproducibly generated and controlled in a pulse power device. This is the Thunderbird device or the Proton-21 device. Okay, so you have the Proton-21 device in Kiev, and then here in the United States, we have the Thunderbird device. So it's called Proton-21, the original device in Kiev, Ukraine. The one in the United States is Thunderbird. Thunderbird. I like that, Thunderbird. By the way, I hope my audio is getting better. Please let me know in the comments. I'd appreciate it. All right. Electromagnetic energy in a single short pulse into a relatively small volume along the central channel of the target, producing extremely dense plasma. We reported the results of experiments at our pulse power facility IVR1 in Kiev, Ukraine, that uses 0.5 megavolts, that's 600 megavolts, producing a 40,000 kiloampere 20 nanosecond electron beam pulse to strike a submillimeter anode target. Okay, the one that they have in the United States is more powerful, much more powerful. But even then, let's just go on. The principal scheme of the high voltage pulse power device and its simplified electric schematic is shown in figure 1. Ben Rex, if you're listening, this is for you, buddy. This is in the video description if you want to read this. Those interested in reading this. Very simple. In order to spread electrical schematics, you can see this is conceptually this is a very simple device. It's just brute force. Okay. I'm just going to read this for you, Ben Rex. Okay, it says here, where you sound like you're underwater, you're scrolling. Okay, that's when I scroll. Sorry about that. The primary features of the pulse-powered device are the capacitor energy source, the vacuum inductive storage system, the set of plasma erosion opening switches, PEOS, and the relativistic vacuum diode, RVD, the relativistic vacuum diode. The vacuum systems of the RVD chamber and the inductive storage are combined and maintained at a base pressure of 5 times 10 to the minus fifth torricelli during the shot. The primary function of the pulse-powered device is to shape and compress the voltage pulse from the main 3 microfarad capacitor charged to 50 kilovolts at 3.75 Kelvin. I think is that room temperature or 100 degrees above room temperature stored energy? Oh no, 3.75 kilojoules. I'm sorry, I totally messed that up. It's getting late. It's not Kelvin, that's kilojoules. Sorry, guys. Oh boy, it's getting late. But I'll push on here. The primary function of the pulse power device is to shape and compress the voltage pulse from the main 3 microfarad capacitor. Okay, that's not a particularly large capacity, but 3 microfarad capacitor charged to 50 kilovolts. To charge a capacitor to that high, that is impressive. That's 3.75 kilojoules of stored energy. Pulse compression is performed by an array of 12 plasma opening switches axially arranged around a solid central conductor cathode and operated from a separate capacitor bank. After the main capacitor and PEOS capacitor bank are charged with negative polarity, the spark gap switch for the PEOS is triggered and plasma is generated in the gap between the vacuum inductive storage system and the grounded outer chamber anode, creating a low resistance short circuit bridge. A few microseconds later, the spark gap from the main capacitor is triggered. The capacitor starts to discharge, accelerating current in the vacuum inductive storage system through the short circuit bridge to the ground, sustained by plasma in the PEOS region. An additional microsecond later, the resistance to the plasma bridge in the PEOS region abruptly rises by orders of magnitude on a nanosecond timescale, effectively disconnecting the short circuit plasma bridge. The inductively stored energy is promptly delivered to the RVD, that's the relativistic diode, inducing a very narrow 20 nanosecond 0.5 megavolt voltage spike. The generated electron beam is relativistic with electron velocities at 0.86 c. That's 86% the speed of light. With a gamma, I believe that's a Lorentz factor of equal to 2. And estimated peak power of 12 gigavolts. Well, thank you. I can't believe Jordan's still listening to this. And I don't believe that he's just being sarcastic here. Independent of the YEC models, this is just interesting nuclear physics. So, I'm trying to temper expectations because, there's a lot we don't know. But if we can generate heavy isotopes in the ratios we see, that'd be interesting. In fact, Walter Brown, who's combed Adamenko's work, and I'm giving it a second over, it seems that the natural state, some of the experiments would put it in the background, ratios automatically. We don't know the reasons why. And this accords with an experiment, actually an observation. Andrew Snelling took some supposedly old rocks, had a separate laboratory date them. They were dated as old, but there were different ratios among the parent and daughter products. They each gave different ages. They're still old, okay? I was at that meeting when he was talking about this. He said, this is still problematic for young Earth creationism, but the good side is you have different the daughter and parent products don't align between the isotopes that were examined. And it seems that the natural generation of these ratios seems to be when you have these experiments, depending on the target that you hit, it comes out that way. That's the preliminary, my preliminary reading from stuff I read a while back. So take that with a grain of salt. I will gladly retract it if that's not the case. That's just my recollection. And like Joe Biden, I'm subject to Joe Biden moments. I could be misremembering what I read. So I'm just pointing that out. But thank you for the comment. And the Oclo thing, the Young Earth Creationists have a variety of explanations for that too. But I'm just going to work through this. And I do want to say, okay, it'd be improper for me to I'm not, I will disagree with Jordan K here, but I would encourage the readers to take it very, very seriously. Anytime he objects to something, it's like, okay, it's an area we got to deal with. It would be improper for me to dismiss it. So just let me back up a little bit. We need to respect his objection. There are definitely some objections from the evolutionary community, that I dismiss. Dave Farina's classic example. Anytime that Jordan or John B or Mr. Jetty 89 will say, hey, Sal, I don't think that's right. That's on my list of things we need to deal with seriously, okay? My attitude toward Dave Farina, it's like anything he says, I'm going to laugh at. I'm going to find something to laugh at. But when Jordan, John B, or Mr. Jetty raise a concern and disagree with me, guys, please take note. That will be an area that the Young Earth Creationists will have to deal with, and it could be a serious problem. On the other hand, I'm trying to give you some stuff that that I think is favorable to our side of the issues here tonight. So let's go on here. This is incredible. You just get this pulse of electricity. You get the electrons to get up to 86% the speed of light, and they're experiencing time dilation. The gamma factor of 2. It's incredible. But, okay, so this is a picture. They have a little like target here that they send the electron beam to. I hope you could see my little mouse cursor. And when it hits, it'll blow it apart, and you'll get a deformation like that, and stuff splatters all over the place. And this is what they call the big circle there that looks like a communion wafer is the collecting screen. So when it hits, it splatters this against the collecting screen. And they're able to examine all the elements that come out of the experiment in this. So and the rest goes through how I'm sorry, let me turn this off. When I scroll, I get that munchkin sound. Then they detail all the grueling experiments to be able to determine the composition of the elements on that accumulating screen. They use all sorts of analytical methods to detect the new elements. Now, other papers that they have had, okay, so we could say contamination, this or that. The thing that really impressed me, and it's one that Vostosky, his work in Ukraine, would also be interested in. It's when they did this experiment, they take this really high-powered, it's really high-powered in the sense it's just concentrated. I mean, I guess if it hit me, it'd probably singe me here. Hopefully I wouldn't die in the process. It'd probably, if you wanted to pierce someone's ear, I guess you could use, I'm just kidding. they're just able to focus all this energy. They did this on cobalt, and they noticed that it had less emissions, radioactive emissions. And Jordan, if you know offhand, is it a gamma emissions? I think it had. So they ran the, I guess the like a Geiger counter type device on this before the experiment. After the experiment, it reduced the rate of emissions by half. So this is a very interesting nuclear transmutation. Why it would do that, we don't know. Okay, so we do know that, for example, photodisintegration, I believe it's cobalt 60. I'm sorry, cobalt 60. And I don't have the paper handy. Apologies for that. So we know that there is photodisintegration where you can hit a nuclei, and there's a Wikipedia article on this on photodisintegration and photonuclear processes. It'll detail what can happen. So definitely you have enough energy to at least do a photonuclear process. Whether it involved the exotic mechanisms that they're talking about of lowering the Coulomb barrier, we don't know. So, this is one of the things you can have. Okay, thank you, Jordan. Does a beta minus decay emit gamma rays? Pardon my utter ignorance on this. Anyway, so we don't know, this is the thing when you're throwing this much energy, when you're throwing, thanks for your replies. Thank you kindly for this. When you're throwing so much energy into the system, is the reaction you're getting a photodisintegration, which is a known mechanism? Is it really this for lack of a better word, this electron configuration lowering the Coulomb barriers? See, these are things that it's going to be difficult to uncoil what mechanism. Any number of mechanisms could be happening. Could it be like, as in the exploding wire experiments, where you actually have some fusion, kind of the old-fashioned way of just powerful collisions? Or what they really want is to have the natural low-energy nuclear reaction using high energy. Use high energy to make a dense electron, a dense electron region, electron-dense region, and then actually lower the Coulomb barrier. So in that sense, it's a low energy reaction. That's, we're going to get into semantics over what's low, high, and cold and hot. Okay, it's going to be way more subtle than that. Are we actually creating an electron configuration that that lowers the Coulomb barrier? So I'm going to now go into the technical paper, and we're at 1 hour 45 minutes. I think I could get through kind of the essentials of this. I want to acknowledge my distinguished colleague, Mr. Jetty 89, who does work on an accelerator, the Microtron accelerator. He's like the smartest guy I've ever encountered in my life, on the internet for sure. He had walked me through this paper. So let me show you. There are two papers involved. One is by Adamenko and Vostosky. Vostosky is a very important character. He if he's a department head at Taras Shevchenko University in Kiev, I think he's a very senior position. I've heard reports from Dr. Edmund Storms, who's also a respected nuclear physicist, that Vostosky's a hero because he uses, about the Chernobyl thing that happened where that nuclear reactor had a problem. I guess it was a meltdown or something. I don't know all the details. They had a lot of radioactive waste, and Vostosky found bacteria that could remediate it. He became a hero in Chernobyl, and he's still a professor. And you know, he's in the Ukraine National Academy of Sciences, so he is respected in that country. Here, stateside, we think that that's crankdom, but you know, this whole thing about condensed matter, lowering the Coulomb barrier is very interesting, and because of the NASA research at in Ohio recently, the 2020 paper, and I don't know if I linked to it in this video description. It's called Lattice-Enabled Nuclear Reactions. They definitely they're claiming they're able to lower the Coulomb barrier by the electronic configuration. They were using exotic metals like erbium. ER is the is the designation in the chemical designation. There were other experiments in 2020. Plus, I saw another one at Lawrence Berkeley accelerator. I have to get all the papers in line, but the interest in lowering the Coulomb barrier in the condensed matter state rather than the plasma state is of interest. So I'm going to read Vostovsky's paper. Let me bring that up. Adamenko and Vostovsky. Let's see. Let me just kill some windows. This is the theoretical paper in 2004. Mechanism of synthesis of superheavy nuclei by the process of controlled electron-nuclear collapse. And as I pointed out, for elements above, like say 137 or 170, I cited the MIT paper, news announcement that talked about for the very high atomic numbers, you can get spontaneous electron-nuclear collapse. So that's interesting topic in and of itself. So this whole idea that Adamenko came up with was actually inspired by the study of astrophysics and something called Fermi gases, relativistic electron Fermi gases. Now, my only encounter of this in graduate school was in statistical mechanics and thermodynamics, the very last class. You know, most of the class was just dealing with ordinary earthbound thermodynamics and statistical mechanics. And we had already gotten our final exam and everything handed in, final homework. So this was just a courtesy lecture. You'd think in a courtesy lecture, some students wouldn't show up. We all showed up for the last day of class. Okay, so the grades were basically in, but the professor wanted to give a lecture. Students were just kind of at the edge of their seat because this was going to be incredible. So we studied things like Bekenstein radiation and all these other kinds of entropies. And he talked about this relativistic Fermi gas that happens in I think in neutron stars. And Mr. Jetty reminded me that the Fermi gas doesn't happen in ordinary contexts. But that inspired some of the study of changing electron configurations to lower the Coulomb barrier, and it was a paper by Migdal. So some of the stuff that were this idea of changing electron configuration by using high densities of Coulombs, high densities of electrons in a small confined space, was inspired by these by a paper on Fermi gases and pions, and I don't get it. And in fact, let me show it to you what the original paper was. Mr. Jetty can read this in the original language. He's a very talented guy. I just can't, you know, I can't promote his abilities enough. But let me show you the paper. I had a hard time getting it, and I had to use a I had to make sure I had to wait till it loaded, so my microphone doesn't go funny. I had to use a Russian to English translator to do this, and I just want to, just for a little bit of fun, let me get the Google translator here. So this is the paper. I had to dig this up in a Russian journal. I don't know how I got it. So I just wanted to show, I was really determined to learn more about this. All right, it's like, I don't read Russian. So thank God we have translate. I can translate Russian to English, and then I get this thing called a Google Translator. And I just want to show this. This is really kind of cute because, okay, so maybe I'm easily amused. So what I would do is I would just cut and paste. And there you get the translation. In a sufficiently strong external field, rearrangements can occur okay, so it's not going to be a perfect translation. In a sufficiently strong external field, rearrangements can occur in vacuum, similar to the usual phase transition. The transition occurs when the energy of individual particles or pairs in an external field is converted to zero, and the spontaneous production of particles becomes possible. For this, the energy gain of the particle in the field must compensate for the rest energy, et cetera, et cetera. But the nice thing about the Google Translator, it'll give you kind of an English version of Russian. Wie das Tatno silnom Vineshem. Okay, I'm not going to try. You know, the only Russian I know is vodka. The only Russian I know is the word vodka. So, but that was the paper that was in Russian that talked about all of this, that inspired Adamenko's works. So now I'm going to read Adamenko's work. He's going to reference it. And in other works than the paper I'm going to read by Adamenko, he specifically cites Migdal's work. So he's not applying Migdal directly. You know, his system, you can't get that sort of relativistic Fermi gas. And I want to credit Mr. Jetty 89 for pointing that out, because he helped me. He read this paper and helped me try to understand it. And Mr. Jetty, if I'm misquoting you, apologies. Feel free to type something in the comments to straighten that out. So I want to acknowledge that I didn't figure out what the meaning of this paper. He was very helpful in helping me get through this. So now to Adamenko and Vostosky's paper, Mechanism of Synthesis of Super Heavy Nuclei by the Process of Controlled Electron-Nuclear Collapse. This paper presents a brief review of the existing approaches to creation of super heavy nuclei in collisions of heavy nuclei to overcome the Coulomb barrier or through the pion condensation in the nucleus volume. A principally new approach to the creation of super heavy nuclei based on the stimulation of a self-organizing collapse of electron nuclear systems is analyzed. For a neutral atom compressed by external forces, a threshold electron density is shown to exist. If such a density is reached, a self-organizing process of electron downfall to the nucleus starts. This process is exoenergic and leads to the formation of a supercompressed electron-nuclear cluster. The higher the charge of a nucleus, the lower the threshold of the external compression. It is shown that the maximum binding energy shifts during such a self-organizing collapse of the electron-nuclear system from A-opt approximately 60. Now, Mr. Jetty says he thinks that's the atomic number or the nucleon number. I'm sorry, Mr. Jetty. Nucleon number. So that'd be 60 is what? Cobalt 60. For uncompressed substance to the area of high mass numbers, A-opt 200 to 2000. Whoa. Good night, Rebecca. Thanks for dropping in. I guess you won't have insomnia tonight after all this. I'm sure my lecture has helped put you to sleep. So sweet dreams. Take care. God bless you. Okay, so A-opt, that's mass, that's the mass. 200 to 2000 could render the synthesis of super heavy nuclei to be energy efficient. And as I pointed out to that MIT experiment earlier, not experiment, yeah, the MIT experiment, they're trying to confirm that atomic numbers, I'm going to get confused between A and Z here. Atomic numbers are Z, from 137 to 170, you will get spontaneous nuclear collapse. What they're saying here is you don't need that. If you have a sufficient electron density and certain other things going on, you'll also get that. You don't need to get all the way up to 137 and atomic numbers 137 to or 170. The MIT paper gave both numbers. I don't know which one. I'll go with 137 for now. It'll happen spontaneously at 137. If you're down to, like, say, atomic number 20, 30 or so, you can get it if you have enough electrons plus some other conditions. Now, what Migdal did was describe having enough electrons, and you get pions in there. Relativistic Fermi gas, you'll get this lowering of the Coulomb barrier. Now, the thing about Migdal's paper, obviously, we're not able to create those conditions here on Earth. We have to kind of just examine the calculations. But this is what Adamenko extrapolated from to try to do this with electrons. Synthesis proceeds through the absorption of other nuclei by the collapsed nucleus. It is theoretically proved that the synthesis efficiency is ensured by both the width reduction and increased transparency of the Coulomb barrier in the extremely compressed electron-nuclear system. The release of binding energy through the absorption of nuclei by the electron-nuclear collapse clusters may result in the simultaneous emission of lighter nuclei. It is assumed that just such a mechanism of synthesis explains the creation of other super heavy and other anomalous nuclei observed in the experiments carried out at the electrodynamics laboratory Proton-21. The Proton-21 laboratory, Kiev, Ukraine, and we have the higher powered version of it here in the United States called Thunderbird, which we're trying to actually do make a fusion reactor with. The Kiev Proton-21, they did 15,000 experiments to do a variety of these things, and this is where they're claiming they're able to create all the elements of the periodic table. I would hope the Thunderbird facility can do the same. To be fair and to give proper caveats, the Sandia National Labs tried to do this. They're claiming that they haven't eliminated contamination as an explanation, and I have, to be responsible here, I have to point that out. Okay, now, as I said, I definitely think that the energies involved could do photodisintegrations. You can get transmutations that way. Wouldn't surprise me if that was the mechanism that they were able to remediate cobalt. So, I'm just throwing that out there. I think to be responsible, it's my responsibility to tell you there are people that have been critical of the results of the experiment. On the other side of that, we do have highly qualified people in George Miley and Novikov, who are also at secular universities, and their papers on the electron beam were accepted by the American Physical Society. That's the premier physics organization here. So at the very least, they feel, even if they're ultimately wrong, they've certainly done a lot of good due diligence to try to justify their experimental claims. So let me just kind of peruse this paper a little more, and then we'll wrap it up for tonight. One of the most important parts of modern physics is the study of anomalous states of substance. The creation of anomalous and super heavy nuclei is of particular interest for science and practical applications as well. The creation of super heavy nuclei by the collision of accelerated heavy nuclei is carried out in several laboratories and requires unique heavy particle accelerators and the huge financial and material expenses. No kidding. The super collider, anyone? Inefficiency of this technique and the fatal problems with the interpretation of results are the consequences of the method's inherent drawbacks. Basic concept of the method of creation of super heavy nuclei via collisions of heavy particles has a direct force nature and requires to collide two heavy high-energy nuclei by overcoming the Coulomb barrier, which creates a compound nucleus with the mass close to that of the colliding nuclei. It is easy to prove that super heavy nuclei, based on this concept, is extremely inefficient and limited. Below, we present some relevant reasoning. A very small probability of the frontal impact of the nucleus accelerated up to the high energy to overcome the Coulomb barrier results in a very small probability of the formation of a compound nucleus. If we compare the synthesis cross-section of a super heavy nucleus, a synthesis cross-section is kind of like the probability of something, relative probability. Cross-section equals 10 to the minus 10th barns, and the ionization cross-section of target atoms, 10 to the 8th barns, it becomes clear that the overwhelming part of the kinetic energy of such a nucleus is spent for the ionization of the target atoms. A heavy compound nucleus synthesized from two lighter nuclei with a proton-neutron ratio close to the normal is deficient in neutrons and has a great surplus of protons. A too low neutron number renders the nucleus to be extremely unstable and unobservable because of its short half-life. The high kinetic energy of relative movement, which is necessary to overcome the Coulomb barrier, plays a negative role for the formed compound nucleus. This excessive energy results in the overheating of the nucleons of the compound nucleus, fast emission of neutrons, protons, and clusters, and nucleus decay. As a result, the extremely small amount of super heavy nuclei is formed and detected. The typical detection rate of nuclei for Z approximately 1/12 to 1/18 by their decay products does not exceed 1 nucleus per month. 1 nucleus per month. The number of background events in the system is about 10 to the 12 or 10 to the 11th to 10 to the 12th. Naturally, such a detection efficiency makes any detailed study of such nuclei and furthermore their use impossible. In particular, the half-life measurement error for such super heavy nuclei is tremendous. Moreover, the factors become more and more essential with increase in the charge and mass of synthesized superheavy nuclei. It's clear that these circumstances impose heavy restrictions on the synthesis of superheavy nuclei and make the formation of even a single nucleus with A greater than 300 by the collision-based technique extremely hard. It is obvious that such an approach is not suitable for the creation of a macro quantity of superheavy nuclei and their practical use in particular. So he's just kind of laying out here why we want to use something other than these massive super colliders to synthesize element for physics study. Now, just as kind of, I had a boss I was working for, he said, yeah, you know, the physicists have talked about building a particle accelerator that could orbit, that would be like the ring of Saturn, sort of a ring around the Earth in orbit. They could finally build something big enough. I'm like, yeah, right, in your dreams. But this is what it would take, you know, this is some of the things the physicists envision, things of that scale, to be able to conduct some of their experiments. So Adamenko and Vostoysky are suggesting an alternative. And I'm going to try to cover the alternative as best as I can. I'm going to stumble through this. I mean, I may be misreading this, but I'm just going to try. Okay, so for those who are more knowledgeable in this than I am, the paper is there. All right. In the 1970s, 80s, A. Migdal and his colleagues considered the prerequisites for the creation of a quasi-stable super heavy nuclei with charge and mass number in range from Z to approximately 1600 and atomic masses from 3,000 to 200,000, and the creation of anomalous superdense nuclei, Z100. As a basic mechanism of nucleus stability, Migdal considered the influence of a pion condensate in the volume of such nuclei. Okay, Migdal's paper was that Russian paper I showed. So that's why this is important. That's the foundational paper, and it was written in Russian. In brief, the idea of the pion influence on the stability of a nucleus looks as follows. The pion stabilizing a superheavy nucleus may be formed in the reaction of spontaneous decay N going to a proton plus a negative pion. This reaction may take place only in the very deep potential well formed by protons in two types of nucleus. In a superdense nucleus or a nucleus with high charge, Z much greater than that number there. And I would say that would be Z in the range of like 100 to 1600 in the above paragraph. First, the negative pions screen a part of the Coulomb potential created by the protons. Since the total number of protons exceeds the number of pions, such a mechanism, however, may not provide the full screening and final stability of a nucleus. The final stability of a nucleus in the presence of the pion condensate is provided by the specific quantum mechanical square law effect of attraction. This attraction does not depend on the sign of a charge and occurs when the energy of a particle, a pion, in the very strong Coulomb field of protons inside a nucleus exceeds the rest energy, mc squared. M pi c squared, that's the mass of the pion, times c squared. Yes, echoes of Einstein here. For the average distance between the protons inside a nucleus, and that's given, I'm not going to read it, only light particles, pions, may provide such an attraction. Light particles. It is obvious that the attraction of a light pion to several neighborhood protons is equivalent to the mutual attraction of these protons. On the other hand, heavier protons at the same distance may not provide such a nonlinear mode of mutual attraction. Hence, each pion stabilizes as a superheavy nucleus twice, as a negatively charged particle and as a lighter in comparison to a proton particle participating in the specific quantum mechanical interaction. Okay, this is what I did not appreciate. They said there's an attraction independent of the charge. It's a quantum mechanical phenomenon. I'm just like, wow. So you can bring these, if you have that negative pion in there and it has to be light. By the way, an electron is light. So I could see where Adamenko is going here. You have that light pion particle. You have the protons that are there. And under certain circumstances, you'll get this mutual attraction between the two positively charged nuclei. You basically circumvented the Coulomb barrier through quantum mechanics. That is just like unbelievably cool. That is like unbelievably cool. So then he's going to go and describe a lot of Migdal's paper here. This is just like a really cool concept. You can lower the Coulomb barrier, one with the negative charge, but then getting a charge-independent method of attraction. So it says here, the collapse of the degenerate electron gas in the Coulomb field of a nucleus is analogous to the phenomenon of gravitation collapse of an astrophysical object with a mass being more than the critical one. And the shell of a degenerate relativistic gas is neutralized by the charge of nuclei. Okay, these are, again, I think these are the Fermi. He's making an allusion to the Fermi gases that I had that one class on in statistical mechanics. This is really cool physics. So I'm just going to keep skipping over. Okay, so now it's this section. He talks about the mechanism, threshold conditions for electron-nuclear collapse of a heavy nucleus in a degenerate electron plasma. Okay, this is the Fermi gas, I think. Okay. And so this, again, is not in Earth conditions, but there's something to be learned here that Adamenko is going to apply in his Proton-21 and his Thunderbird experiments. You all can, read through this. I've not heard of the Wigner-Steitz elementary cell that's mentioned here. Okay, there's stuff here that's over my head for sure, but I want to learn this stuff. This is very interesting to me. And I'm sorry if I opportunity here to take a swipe at evolutionary biology. You want to see what real science is? Read this paper. Those phylogenetic diagrams, they don't work anyway. They don't tell the story of the evolution of complexity. And it's really uninteresting to me from a scientific standpoint. It's mostly useless, even if true, and I don't think they are true anyway. So anyway. Oh, there's the rock equation here. Oh boy, it's going to be a little hard. The one thing I understand in this equation is UF. UF. Right here, it says UF. 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 The effective potential energy determining the movement of an electron with full energy E in the field potential. Okay. UF. mean, to understand this, I think this would take months of study on it. I mean, obviously this is so deep. This would take months of study to really appreciate and comprehend. And eventually I would like to comprehend this. This is just interesting physics. So I said I'm going to be migrating outside of biology. Probably the better thing to say is I'm going to be changing the proportion of what I study, increasing more of the physics side, lessening the biology side, because physics really is the love in my heart is for physics. It's very hard and it's tedious, as you could see, but there's just, I don't know, there's something very ennobling about it. That's very beautiful. Biology has its own beauty when it's studied in terms of the complexity of its design, but the biology discipline, on the most part, doesn't have the design perspective, and that kind of just takes away the beauty of it. They're very bottom up, not top down. You know, top down meaning, you know, what's the overall function and what's the purpose and what are all the salient features of this, rather than just talking about, you know, molecules and parts. It's like, if you know, maybe to compare it, it's like trying to describe an airplane just by giving you a parts list. It's different when you actually describe the airplane in terms of what it does on the whole. It can fly, it can take off, it can transport. And a lot of biology is just parts lists. It's not kind of a functional description. So anyway, this paper is not trivial, as you could tell. I would have to relearn. I'd have to relearn a lot, and I'd have to learn lots of new things to really appreciate what's here. This whole stuff about the quantum mechanical attraction between protons, if you have a light negative charge, that's news to me. That is really cool. I've never heard that in any of my classes. But that's an incredible way, if true, to reduce the Coulomb barrier. And if you just see this, this is real science. This is good science, way better than evolutionary biology. Okay, so now he's still, I guess he'd covered a lot of like the pions and then electrons in like would be found in a neutron star. Now we're trying to kind of port some of this knowledge into an earthbound system like the Proton-21 device or the Thunderbird device. I'm just going to read the summary here and try to wrap it up. Oh, this is so way better than way better than evolutionary biology isn't saying a lot. Oh man, talk about sticking a knife in and twisting it. It is way better. This is real science. Okay, so we have proposed a theoretical model of a threshold type self-similar electron-nuclear collapse gained at reaching the energy density in the electron plasma of about 0.65 mega electron volts per electron, which really isn't a lot, okay? I mean, compared to your super collider, this is like uh, this is child's play compared to the super collider. A lightning strike could, in principle, generate, I think, electrons of this, given that the electron lightning strikes could generate 300 million volts, 0.65 million volts is not that much, which corresponds to the high critical density of degenerate electron gas. This density is very high as compared with the value of Ne, of 10 to the 24th per cubic centimeter, typical, for example, of the natural state of the conductivity zone in metals. At the same time, the value NECR appears to be less by many orders of magnitude than the final density of 10 to the 36th to 10 to the 37th cubic centimeters, which is automatically reached after a preliminary compression in the self-organizing process of the formation of the collapse state, and is comparable to the intranuclear density of nucleons. In the collapse state, the direction and probability of nuclear reactions are changed significantly. The influence of the Coulomb barrier is greatly reduced, and the spontaneous synthesis of super heavy stable nuclei becomes probable. This approach differs basically from the forced method of nucleosynthesis. It is very important that the formation of the state of electron-nuclear collapse of a nucleus is based on its own electron system. Thus, this process is adapted to this nucleus, the nucleus in the best possible way, and is a coherent adiabatic process. Brain bug. I'm actually a night owl, and that name sounds familiar. I should know who you are. We're talking about Young Earth Creationism and these experiments in nucleosynthesis where electricity can change nuclear structure. I'm postulating it can account for the proportions of radioisotopes and give the appearance of age. But this is really cool nuclear physics. And it does touch on the topic of cold fusion. And I went through a lot of the experiments. Many of them that are recent, they don't like to use the word cold fusion, but that's what it is because there's such a bad reputation surrounding it because we had a lot of cranks. But there has been relatively low energy fusion events that experienced by NASA and others. The experiments are becoming quite numerous now. And there are other forms of transmutation of elements other than fusion experiments, including photodisintegration, photonuclear processes. There's even Wikipedia entries on photonuclear processes. We've had an experimental observation of neutrons from lightning strikes. That's an example of where you get just enough electricity, you can change the atom. And that's not conventionally what you think of how you can change nuclear structure with electricity. This obviously has relevance then to whether you can change a radioactive isotope to something else. And we definitely can do that with the photonuclear process. But there may be other processes. This one involves like taking four copper nuclei and making a uranium. And the experiments here claim that we can do that with electricity. The mechanism, the device that was used was in the Ukraine. Sadly, you know what's happening in Ukraine. The mechanisms that can do that, there's a device called the Proton-21, what I call the Proton-21 device in the Ukraine. The Americans, in conjunction with the Ukrainians, built a Thunderbird device. It's on the order of a $10 million device. Here near the Oak Ridge National Laboratories, we have some very excellent scientists working on it. And I cited also other experiments that were just kind of taking electricity and passing it through tungsten or some other wire and you're able to get nuclear transmutations, and this is no longer in doubt. You could argue that these are hot fusion experiments or high energy, and when we get into semantic games, basically what happens, it facilitates it, what this paper does is try to say that the electrons in a condensed matter substance, like say, ordinary copper at room temperature, or like say at 100 degrees, I think it doesn't melt at 100 degrees. In that state, the electrons are important. When you bombard it with electricity, it will spontaneously trigger this quantum mechanical attraction between positive nuclei. And I had just read that part of the paper, and you can get spontaneous, with some other conditions, you don't need high energy then to merge the nuclei. You have a low energy nuclear reaction that is at least in principle capable of making isotopes in proportions that we have interpreted to be old ages. And because I have actually agreed with evolutionists that accelerated nuclear decay is not a very good explanation for what we see. It incinerate the Earth. It would kill us because of the potassium. I believe it's the potassium 40 in our bodies. Our blood would boil. So we don't want to appeal to that to explain some of the radiological phenomenon. So that's why this presentation has been so long. I've actually been combing through all the experiments in mainstream and also very high profile peer-reviewed scientific journals like the American Physical Society, Nature, Science, and then of course some lower ones like Plasma Physics, and even some journals over there in Russia and the Ukraine. I went through the qualifications of the professors involved, and at least from due diligence, their experiments are credible in that sense. Whether they're ultimately right will remain to be seen, but certainly in terms of due diligence, there's been a lot. You could tell that they've exercised a lot of due diligence. Now, unfortunately, there are a lot of cranks and hucksters in the cold fusion community, and that's really unfortunate. They hustle for money and investments, same old game, and that's really unfortunate. But there have been continue to be relevant and interesting experiments. I cited one with lasers at low power, changing plastic, being able to change the molecules there. They leverage again this phenomenon of what they call electron screening to lower the it takes energy to take two positive nuclei to merge. There are ways to get around that, and I was describing a lot of the theory and experiments that are demonstrating that it's probably feasible. So, and I'm just wrapping it up at this point. That's why I'm at the summary of this paper. In the collapse state, the direction and probability of nuclear reactions are changed significantly. The influence of the Coulomb barrier is greatly reduced. And the spontaneous synthesis of super heavy stable nuclei becomes probable. This approach differs basically from the forced method of nucleosynthesis. It is very important that the formation of the state of the electron-nuclear collapse of a nucleus is based on its own electron system. Thus, this process is adapted to the nucleus in the best possible way and is a coherent adiabatic process. The consequence of such, I think adiabatic, that means you're not adding heat, adiabatic. Okay, that's an interesting term. All right. The consequence of such a formation of the state of collapse are diverse and evident. Okay, so the fact that it's adiabatic is interesting, because if we're having these nuclear reactions and the reaction itself is not creating heat, okay, so maybe all the external forces to generate the electricity is obviously a hot process. But if you're not adding heat, you're actually having you could have accelerated nuclear processes effectively, not what I call the isotropic nuclear acceleration that the YEC community largely embraces, unfortunately, what I call isotropic accelerated nuclear decays, where you incinerate the Earth, you incinerate people. You incinerate the Earth long before you incinerate people. This sort of quote unquote accelerated decay, it's not really decay, it's transmutation is a better term, is adiabatic. You don't generate any heat. You don't generate, so this is a very interesting transformation if it's adiabatic. Is going to be really cool then, because then you could circumvent the heat problem. I'm sure Jordan's probably asleep now, but this is why this is exciting also. Okay, so let's go. So the consequences of such a formation of the state of collapse are diverse and evident. A part of them is connected with the possibility of the synthesis of super heavy nuclei with masses exceeding those of the transuranium isotopes by many times. Such a synthesis becomes possible because the energy minimum of the system of electrons and nuclei shifts during the fast formation of the state of collapse from the area of mass numbers A opt 60, it corresponds to the ordinary nuclei and a low density of electrons, to A opt greater than 2,000 to 3,000. Wow. This shift ensures the energy efficient synthesis by nuclei absorption and creates the basic prerequisite for the formation of stable super heavy nuclei. The high efficiency of the synthesis is determined by the fact that for a nucleus in the state of electron-nuclear collapse, the Coulomb repulsion appears to be greatly weakened because of the strong screening of a nucleus field by the degenerate compressed relativistic electron gas. Yes, Wesley. Yes, I know. You know, the Young Earth Creationists have been bashed over the head, and I think sadly, rightly so, over the heat problem. There are two heat problems. Erica Gutzik-Gibbon has highlighted one of them. One is associated with meteorite strikes. The other is accelerated nuclear decay. So unfortunately, Rebecca earlier, who was here, said she had to turn in. I wish she had stayed for this punchline, because if Erica and I were having a discussion, I'd say there is an out. This adiabatic nucleosynthesis process, it's adiabatic. That means you don't change, you don't add heat or remove heat from the system net. Okay, obviously you have all this external heat applied at the front end, like, you know, like with the lightning strike, but you're not, like in a typical fusion reaction, you're not creating all this energy like a thermonuclear weapon, nor are you generating all the electricity, all the energy by a nuclear decay process. You're getting an adiabatic transformation. So yes, ha ha, I like that, ha ha. So again, this is why it's helpful not to just totally dismiss when an old Earth creationist puts forward an objection like, oh, this is going to be problematic for accelerated nuclear decay. Maybe we need to look elsewhere. And see, now we may have an explanation, if my poor Joe Biden memory serves me correct, which is questionable, that some of the electrically induced transmutations will actually give you the parent and daughter ratios that we see in old Earth rocks. You know, particularly the rocks like the moon rocks or the rocks that we have on Earth that give us the age of the Earth. Okay, so there could be ways to modulate that proportion, but it could explain it, and it could possibly explain the funny anomaly that depending on the radiometric method used for the long-term stuff, why the dates are, even though they're generally old, they're discordant enough that it has to be accounted for theoretically. You can't just say this is just an error bar or something. I think it's beyond the error bars. That's a separate discussion. plus you've solved the heat problem. And as I said, independent of just trying to prove the Bible true, we have secular reasons to invoke a young Earth. One, the billions of years evolution from a nebula just has a lot of mechanical problems. How do you evolve planets from a circulating disk and planets at very different orbital planes? Okay, that's nasty. It doesn't resolve their angular momentum issues with the sun in this. Okay, there's problems with the differentiated chemistries. I mean, this is all in public literature if you're willing to read it. There's the Earth's magnetic field. There's the faint young sun paradox. In the fossil record, we have the racemic problem of chemical racemization not enough. Same for oxidation. Same for the existence of peptide bonds. Same for any number of chemical things. There's erosion mechanics. There's just numbers of things that are problematic for the old Earth, old fossil record model. That's not to say that there aren't severe problems also with the Young Earth Creationist model. But as I close this out, I'm not going to read the rest of the end of the paper. I think I got to the meat of it there. At least the Young Earth model. Okay, I've been watching this debate transpire, unfold over the last 40 years since I became a Christian. I was a theistic evolutionist, became a old Earth creationist, then a Young Earth creationist. It's moving forward. Evolution, abiogenesis theory is the first thing to fall apart. Now they're at the point they're invoking multiple universes. It started with the Urey-Miller experiment saying we're close, and then people coming in saying, like Francis Crick, Nobel Prize winner, elucidated, Watson and Crick fame, started to suggest extraterrestrials, and same with Fred Hoyle. Now, multiple universes. Tamani, and then also a paper by Kunin, one in the Proceedings National Academy of Science, another paper in Nature, invoking multiverses to solve abiogenesis. That's a state of a field that is in desperate need of miracles. And it's like, okay, if you're going to invoke miracles of multiverses, why don't you invoke miracles of God? I mean, given you see the exquisite design, it seems like an intelligence. Quantum mechanics, one interpretation of quantum mechanics suggests such a being. Okay, so purely scientific. So abiogenesis is failing, eukaryotic evolution is failing, probably other protein evolution of the major families. I've done shows on that. So the fight is between the progressive, as far as I'm concerned, the remaining competition is between the old Earth creationists, ID proponents, versus the Young Earth creationists. I don't think the theistic evolutionists, the ones like Swami Das, I don't think they have a prayer. I think they're just dogmatists at this point. James Tour took Swami Das to task about his endorsement of the oh, great question. Swami Das, Tour, I'll answer this question. Thank you for your question. Swami Das, who was invoking the RNA world, and tore that apart. And speaking of the RNA world, that's where multiverses were invoked. So let me see if I could find it. Brainbug, your question is important enough. I'm going to actually, if you'll give me a couple of minutes to retrieve the information, I'll give you one citation that dealt with the RNA world and multiverses. If you will indulge me, I think other readers would want to hear this. Carter. Okay. Okay, the reference is, I'm going to drop it in the side chat for you. One reference paper this one. Emergence of Life in an Imaginary Universe by Tomonori Tatani. That is in, come on, I'll give you the abstract here. In Nature Scientific Reports. Nature Scientific Reports. Imaginary Universe has all these little pockets of other universes with different initial conditions. They're unseen, they're unverifiable, they're predicted by inflation theory. The Big Bang's in big trouble. So that form of multiverse may not be in play, but I'm sure they can come up with other sorts of multiverses. He does a calculation here just based on the RNA world of 20 nucleotides. And anyone that's read The Stairway to Life will know that that's, you're not going to evolve a protein coding system from a system of an RNA replicator. And Stairway to Life by James Chan and Rob Sadler actually detail the problems. We'd end up with nucleases more than replicators. Nucleases meaning the little cleavers that would cleave the RNAs. That's at least one of the problems, not to mention all the statistical problems and chemical problems like temperature. So that was one. I'll give you the other one by Kunin, who's you recognize that one. I had the privilege of studying under Eugene Kunin's staff at the NIH. And Kunin, so that was in Nature Scientific Reports. This one is, I misstated if I said National Academy of Sciences. It is by Kunin, who heads up a team of 30 evolutionary biologists. He waded into the origin of life question, little, outside of his field, but still he's very respected. 400 peer-reviewed papers, and this is his one. This is Kunin's. They're invoking multiverses. I'm just saying where it went. So now, people are saying that we'd never solved the radiological problem. And I'm not saying that the Young Earth Creationists have, not by a long shot. But we have a bigger spectrum of options to how this might be solved. And that's why I spent now almost 3 hours, or 2 hours and 45 minutes on all the details of this experiment, because one, it talks about transmutation, and the transmutation is adiabatic, so you automatically don't trigger a thermonuclear heat problem, or even what would be associated with accelerated nuclear decay. It's great to hear that word adiabatic in this process. One, and another secular reason for this is that independent of trying to confirm the Bible, it's just purely secular reasons. There's 70 times more abundance of uranium on the continental crust than there is on the seafloor and presumably the Earth's mantle. We'd need a lot of ad hoc explanations to explain for that concentration. If, on the other hand, tectonic activity, which is now believed, or at least strongly suspected, to create electrical activity, you could create these very dense regions of electron density, these pockets of high electron density, and these lightning strikes, because either through the piezoelectric or triboelectric, or who knows what sort of electric effect through tectonic activity, those dense electrons then could be capable of inducing nuclear transmutation. So that's what this show was about. So that's why, on this channel, we're very different from, I'd like to think we've fulfilled we are in a niche where we're not the typical internet debate. I'm just like, how are you going to debate these topics in an hour and settle the problems of the universe? You can hardly get through the abstract and the introduction of a peer-reviewed paper. So we actually do on this channel, I do, and others with me sometimes, will read through peer-reviewed papers, and we'll just slug through it. And if it's boring, it's like, well, that's real science, and we get to learn it and try to understand it. And I find that also reduces a lot of the drama, because it stops being about personalities and he said, she said. We talk about observations and experiments that may resolve the difficulty, and sometimes, many times on many topics, we'll just say we can't resolve it at this time. We don't have enough experiments and observations and enough theory to figure it out, and just say, okay, we accept some things on faith. If the Earth, I reject common ancestry at this point, but in some of my publications and my writings, in my peer-reviewed and secular writings, I will assume common ancestry from for the sake of argument. And I encourage young Earth creationists to start with arguing intelligent design and accepting common ancestry for the sake of argument. Brain Bugger, are you the same guy that studies insects? Are you the guy that studies insects? I visited your channel once, and if that's you, Erica spoke very highly of you. So feel free to ask a few more questions, anyone, before I shut the channel. I'll open it up to talk about anything, but at the 3-hour mark, I think it's only sane to shut the stream down. I really want to thank everyone that's joined us, both live and also on recording. This is grueling, but I think I needed to lay this out there for people to see that there may be avenues to solve the radiometric problem, much more than I mean, what Young Earth creationists have done is say, oh, here are examples where it's unreliable, but then they they tend to suggest, just because you have a few measurement errors, that the whole field is wrong, and that's not going to cut it when some of these science students who are creationists or Christians go through secular school and realize that there's a lot to really wrestle with that is very problematic for the Young Earth model. And we don't do that on this channel because we cater to those people who are to Christians and creationists who are science students at the college and graduate level, and some are professional researchers. And you can't pull a Kent Hovind on them, or there's a channel where a used car salesman is dressing up in a Superman outfit as if he's some super authority, and it's just it's pretty shallow treatment, and uses a lot of rhetorical gimmicks. It's not real science, and not it wouldn't have the staying power for someone who's going to go off and actually study these topics. And it's important that they're equipped, because these could be the new creationist researchers of the next generation. I've had the privilege of doing this professionally for 7 years, working for John Sanford as he's a genetics researcher, well respected in prior to becoming a creationist. He had a very respectable career as a genetic engineer, as a Cornell research professor, and I had the privilege of working for him, studying protein biology. Even though he's a geneticist, he gave me the freedom to study protein biology. So Brainbug, thank you for coming here. I've had secular publications critical of evolutionary biology, one Springer reference work, and then I've also published in medical research on topoisomerases, and then in secular venues, and I hope to continue to, even though I'm a Young Earth creationist and I've been outed. some journals have more tolerant editors, especially those overseas. And I hope to, I don't know that I'll ever be good enough to publish in the physics realm because that's very difficult. So that's just a little introduction to me. And Erica is also my friend. And if you run into her, please say hi. Dapper Dino is also my friend, and Bent Hovind. I mingle a lot with the evolution, and Dr. Dan. I think you know Dr. Dan. I mingle a lot with the evolutionary community because in addition to my physics degree, I was sent off to study biology, and I had to matriculate through a secular biology curriculum, and you just have to learn how to get along with people, and they may be your research colleagues or fellow students. And I'm certainly not as combative as the policy of some other channels. So thanks for visiting Brainbug. And Wesley, as always, it's super to see you. I'd like to thank all the others, and I know I'm going to miss some names. I appreciate the Jordan K, our Reasons to Doubt, dropped in. And Rebecca was here. Cheryl dropped in briefly. Jamie Russell, Paleologos. A lot of people eventually dropped off because this was long and tedious. David Neff was here. So with that, this is a Christian channel. I'd like to offer a prayer for this troubled world. I'll turn off my camera here. Heavenly Father, please thank you for this stream and a world, at least a place and pocket in the world where we can just speculate and think and explore science. There are horrible things happening on the other side of the world. There are wars and rumors of wars. There's famine, there's pestilence. And Lord, if you've commanded us to pray for our leaders so that we may be able to live a peaceful and quiet life, and this is in contrast to the fact that you said the world will come to an end and there'll be terrible things happening, and yet you have commanded us to pray for peace, and maybe judgment day is deferred. May we live long enough in a civilized society to figure out some of the things that we talked about tonight. And Lord, be with us and comfort us. And there are people in this community here on my YouTube channel that are suffering through personal problems, physical problems, ailments, financial problems, worries, and just all the drama that surrounds human life. Please reassure us, Lord, and comfort us, and help this channel to prosper, to explore your work, and to find evidence of your creative power in the universe. And I thank you also, Lord, for the old Earth creationists that have been a part of this channel, even the theistic evolutionists who are Christian brothers like Bent Hovind. And be with us, Lord, and reveal yourself to the world. In Jesus' name, amen. So with that, take care, good night, and God bless you.